am so excited to have Sam Scher joining us today. She's one of my favorite humans and is the principal consultant at LKI Consulting, a geochemistry and applied hyperspectral consulting firm that operates in the mineral exploration and mining industries. Sam is also the creator of the Geochemistry podcast, whose mission is to give a leg up to those that want to know more about geochemistry, as well as to provide a platform for established geochemists to talk about some of the issues of the day in an informal setting for the benefit of all geoscientists. So it is going to be amazing to hear from her today about hyperspectral and geochemistry being better together. So it's going to be an awesome session. Please use the chat. We'll open up the floor at the end for some discussions. And yes, thank you so much, Sam, for joining. It's amazing having you.
Yeah, thanks, Jess. Just for you guys to know, it's 9:20 here. I usually lose it after 8:30 p.m. So I really would love for there to be discussion. I don't know how useful I'm going to be, but I really hope that everybody has something to say. The other thing I just wanted to quickly say is that this talk is definitely geared towards helping people out. How do we talk about this with providers, with your teams, with your bosses, with anybody? And I really just, with this, I want to first give everybody an introduction to hyperspectral, and I want to give everybody an introduction to some of the more conceptual geochemistry. And then we're just going to look at a few things where we're going to marry everything together and just see how the two disciplines really play off of each other. So like I said, those are our goals. And I don't know about you guys, but I always really loved Family Guy, and this episode in particular is pretty funny. But I think that really captures exactly what I'm trying to say here, is that it's really hard to understand all these concepts, whether it's chemistry, hyperspectral, but a lot of times I find that people are trying to explain things to other people. No, there's no minimum level. And I hope after this, for both hyperspectral and for geochemistry, we're closer to that level where we can all start talking and not be confused by terms. Okay, so background on spectroscopy to start. So just some basic slides, and I really want to just quickly credit the team at CoreScan and also Brigitte Martini. A lot of these slides are based on stuff that we all did together for a long time, and a lot of their effort has gone into this, and I'm grateful to be able to present some of this. To start out with, you have spectroscopy is just physics, and to understand this, you have to understand like how to get from point A, which is your light source, whether it be the sun or it's a quartz halogen lamp if you're doing a scanning system, how you get from point A to point B being your rock. And for that, we have to understand the basic physics of electromagnetic energy. We're going to learn how to travel from point A to point B, and what does it do once it gets to point B. Electromagnetic energy. Here, what we're really going to be talking about for the purpose of this talk is visible near infrared through to the shortwave infrared. And that spectral region is between 450 to 2500 nanometers.
Electromagnetic radiation spans an enormous range of wavelengths and frequencies. This range is known as the electromagnetic spectrum. The EM spectrum is generally divided into 7 regions in order of decreasing wavelength and increasing energy and frequency. The common designations are radio waves, microwaves, infrared or IR, visible light, ultraviolet or UV, X-rays, and gamma rays. Spectral geology is the measurement and analysis of portions in the electromagnetic spectrum to identify spectrally distinct and physically significant features of different rock types and surface materials, their mineralogy, and their alteration signatures.
Two things that we have to understand with infrared spectroscopy. First of all, we're going to talk about absorption, whereby absorbed energy affects the fundamental molecular dynamics at energy state from the incoming
radiation, which travels as photons. During absorption, incident energy interacts with the material, and some energy is absorbed, and the wavelength that's reflected is the color that we observe. In reflectance spectroscopy, light interacts
with either electrons themselves or with molecules. And the total energy contained within each molecule in this case is electronic energy, vibrational energy, and rotational energy.
Absorption features are related to various electron movements and behaviors in the V-near, including crystal field transfer, electronic transition, and even color.
The electrons jump to other energy levels. That's going to leave a fingerprint that's recorded as a spectral absorption feature. So over here, for instance, you'll see that it's a very broad absorption feature in the V-near range at about 1100 nanometers. And this is characteristic of a magnetite spectrum. The other one that we want to talk about here is vibrational energy. Hereby, we have energy states that are due to harmonic vibrations. And really what's happening here is you have this incoming radiation that's causing these molecules to, like, in quotes, vibrate. You're going to have stretching, you're going to have bending, you have asymmetric stretching. All these happen in really predictable and really well documented geometries. And these directly relate to the chemical makeup of, in our case, of a mineral. What does absorption, in summary, do? You have incoming radiation that's received by an object. And in this case, what we can see is why are plants green? So you have the incoming radiation is formed from sunlight. It's hitting the leaf. Some of the energy is passing through the leaf, which would be transmission. Some of it's being absorbed in the leaf.
Blue and red wavelengths, and
then some of it is reflected back. And so the reason why then that we see these green colors, when it comes down to it, the diagnostic absorption features in the veneer and swirl, what are we seeing? So we have here all these electronic absorption features that are occurring because of that here. The big ones being iron, so iron oxides would be a big one, goethite, hematite, magnetite, or any mineral that contains iron, you're going to get features that occur here. And then when you get into the shortwave infrared, you'll have OH bonds, the more famous one being at 1400 nanometers. You have water molecules that are at, say, 1900 meters, that's unbound water. And then you have your ALOH features, you could have carbonate features. For instance, if you have a muscovite, so that would be ALOH bonds that occur here at 2200 nanometers, an ALOH bond that's occurring here at 2250 about. And then you have also your 1900 and your 1400 nanometer features. And that's why you see this fingerprint that is distinctly muscovite. Something else I wanted to touch on was just to talk a little bit about the spectrometers themselves and what are they. I think there's just something that I've noticed that's really important for people to be able to talk with their providers about is to understand what exactly is a spectrometer. This is a very simplified rendering of it. So you have your light source, it goes through a slit, hits a mirror, there could be diffraction grating, another mirror, sample, things are reflected or absorbed, and then what you have is it goes back to the detector, eventually getting into your software. The photons, they're reaching this detector at a specific wavelength, and they're going to be converted to electrons that is via the photoelectric effect. These electrons at detector are converted to a voltage, then digitalized, turned into a number by an analog to digital converter, which gives you a digital number or DN. And this is something that you'll hear maybe people talk about or say. This digital number is then going to be summed into a final spectral signature, and radiance will be calculated from this. It's derived completely by just applying the gain and offset values inherent to each sensor to the digital number values. And this is what results in your radiance signature, which then feeds into my next point, which I think is where we're going to start to get a little bit more comfortable in talking about something that maybe people have started to see before. So you're starting here with your radiance signature, and then how do you get to reflectance, which is what people are interpreting, right? The way that you go from radiance to reflectance is by using these spectralon standards, and you just divide the radiance very simply by the reflectance. And for this reason, I think a lot of times we'll see in the field that these like white plates that we have can get really dirty if you're using your Hyperspec or you're working with somebody else that has these very non-white spectralon plates. And so that's a problem, because if they're not a perfect reflector, then you're going to have errors introduced into your data. When people receive their spectral data from, whether it be from a Hyperspec or whether you're going to ask your hyperspectral imaging provider for your hyperspectral data cube, all that data that you're getting is going to be in reflectance data. And what that it's just going to be, it looks like something like this, say, and it's just going to be reflectance either from 0 to 1 or 0 to 100%. And on the x-axis is going to be the wavelength. And that's just what you're going to have. It's really important to be calibrating often. When you're using, say, a Hyperspec program, it recommends that you calibrate every 15 minutes. So it's really important to also talk with your providers about how often they're calibrating, just to make sure that you're having the best data that you can. Because what you really don't want to have is shifts in your absorption features. If you have shifts in these absorption features, then it's not necessarily that you're going to say that, oh no, this is not a white mica, it's a chlorite. It's really just at that point, can you say, is this a paragonite, muscovite, or a phengite? And at that point, the data fidelity is where it starts to break down. One last note, it's just really important that temperature is considered. These spectrometers themselves like to be cool. And so if you're in an area that's where it's really hot, or actually it's just really cold, this can affect your spectrometer and it can affect your data. So it's important to make sure that everything's in spec. And the last point I wanted to make on here is that if one of the ways that you can always make sure that your data is well calibrated and it's all above board is that besides calibrating with the Spectralon, you should also be checking with either a Mylar panel, or you can have redoped standards. And those are just going to have your absorption features at very specific places. And with those specific places all the time be there. And if that absorption feature isn't there, then there's problems with your data. Instrument drift is a thing that you do need to be worried about and you should be constantly thinking about. Moving into kind of this last phase of my little intro to hyperspectral is that I just wanted to talk with you guys just about the different terms that you'll hear, and just to have you guys all at the ready to either ask your providers questions in order to select the best provider for you, or just so that when you're interacting with people and you don't just have to shake your head anymore, you can actually know what they're talking about. The first is the more obvious one, which is spatial resolution. And that's just generally reported as the dimension of the pixel or sample area. We call it pixel size, spot size. And it's just defined as the smallest object that's clearly imaged with distinct boundaries. Over here, I've shown examples of the Landsat and Avira satellites versus a HIMAP system, which is an airborne system. Here you have 30 meter pixels to 20 meter pixels to 3 meter pixels. And this over here is a hyperspectral core image that is courtesy of the Minnesota Department of Natural Resources. This is a piece of core and it's at 500 micron pixel size. So you can see how these resolutions can start to get really impressive. But there's always, I just want to make you a point too, there's always a cost for having higher resolution. Are you going to be losing something else? Are you going to be losing some of the other things that we're going to talk about? It's important to not just focus on spatial resolution, but to also ask these other questions as well. The next one would be spectral resolution, which would describe the wavelength intervals over which each spectral band's measurement is made and determines the ability to discriminate the features. With this, a good way to think about it, this would be a multispectral image. If you were to use a Sentinel or Landsat, you have just a few points over this entire, say, 450 to 2500 nanometer range. And you can see how this is very chunky almost, right? But if you get a hyperspectral image from whether it be Hyperspec, whether it be a Spectrum system, Hyperspec, any of them, now you're starting to get this really fine resolution. And so this is like another one where this has been something that's identified as tau. You know, this is a very fine hyperspectral MGOH feature. And then you can see as you decrease the sampling size of the bands, it's just how much grosser it can be. And now it's just at this point, right? Would you even be able to say that's talc? You would need other information to say that. Another question would be, what's the spectral range? So does it go through the V-near, SWIR, midwave, long wave, or does it just do the V-near, SWIR? It might be important for you to work in those other wavelength ranges. It might not be. And then also this diagram, I think maybe it's a little more tricky to understand just at first glance. But if you look at this, so this is the Landsat satellite, and basically the VNear range, you have one band, you have 4 bands. In the shortwave, you have 2 bands. And then in the thermal, you have another band here. If you look at Aster, you can see something similar happens. And this might be just a regular handheld spectrometer where you're just looking from 500 to 2500 nanometers, and you just have a lot of consistent contiguous bands. So there's no gaps between them. And they're telling you just differences that you can have between doing hyperspectral versus multispectral, absolute mineral identification versus more broad classifications. Do you have clays versus do you have kaolinite versus muscovite versus porphyry? And the last one I'll talk about with these bands, because I think I tend to say band a lot, and so do a lot of people that work in the industry, and we forget that spectral resolution, band, they all kind of fall in a similar category, but not everybody knows what a band is. So a band, when you're talking about this band configuration, and really just to go back, like every one of these would be a band, every one of these little slots here. And so when you talk about that, you want to ask, what's your band configuration? Because you want to know, hey, if I'm doing this airborne survey, am I going to get all my bands in the VNear, but actually have a porphyry system? So the shortwave is going to be really important. I would rather have a lot of stuff in my shortwave infrared as opposed to just having a ton of bands in the VNear. It would be something like this, right? One band could be black, white, monochrome, RGB. Then you'd have multispectral, which is a bunch of bands, about 4 to 20. Then hyperspectral would be more than that. And asking if they're contiguous is really important too. Signal to noise, you start looking at this picture. Can you really see much definition? Not really. You're starting to see better. So signal to noise, you're just looking to see how crisp and how clear is your picture going to be. And the higher your signal to noise, it's going to really improve your ability to interpret your mineralogical information. The last kind of characteristic here that I think is important just to make mention of is you're going to be your field of view or your swath width. And we think of this, I think, more in, say, if you're doing an airborne survey, like how wide is this going to go? But it's also important to consider swath width when you're doing even core imaging as well. All these parameters are going to ultimately affect how you're interpreting your data. And then in terms of when you get an output file, right? When you get an output file, you're going to have mineralogy, you're going to have mineral composition. Sometimes you'll get what we would term at CoreScan as global spectral parameters, which would just be more general, say like you give 2200 nanometer feature, but you don't actually say it's just for white mica. So you might have these that are just these 2200, 2250, 2340. And even though it's not specific for a mineral, you can see larger changes in your data set. So they could still be quite interesting. To here, I included just a bunch of things that you might see in terms of spectral parameters for minerals. You could have an alunite 1480, which looks at sodium versus potassium substitution. For alunite, natural alunites, amphiboles, biotites, carbonates. There's a ton of them that are out there, and they're useful depending on what you have in your project. For every project, are you going to need all of them? No, but it's good to know that there are these things out here that can help you distinguish even more than just, do I have an epitope? You could say, hey, do I have clinososite or do I have epitope? And you could also get structural information like crystallinity that you can do for, say, keylonites. You can do it for white micas, and that potentially could gives you the answer of the orderness of the crystal structure. But a lot of times you can use that as a proxy for temperature for formation. Last slide here that I wanted to make mention is something that you should be asking your your providers, but also you'll see throughout the literature as well. There's mineral mapping, which is more nuanced. You're characterizing individual components of a spectrum to map the distribution of these individual minerals. Or you can do something that's machine learning based, which is more of a group approach. But anyway, point being is that there's different ways that you can interpret this data. Neither is wrong. It just depends on what you want your data to do and what you want, how you want to apply this data. But definitely asking how people are interpreting the data is important. Okay, so moving on, I just want to make mention of a few things in geochemistry that I think are more, instead of here's how you interpret this data using a probability plot. I wanted to bring some fundamental principles to the table just for people to think of. I think for me, geochemistry, a lot of it is looking at some core and being able to think critically about why you're seeing different mineral assemblages. And so I wanted to bring up some of these points so that everybody could potentially maybe have these thoughts next time that they're looking at some core. But I also think doing just some statistics with your data can be short-sighted if you don't have some fundamental understanding about basic geochem principles. So like this table, periodic table in general, it matters. There's actually a lot of information in it. And whether we think about it or not, we're applying things that are summarized in the periodic table while we interpret geochem data all the time. This table is actually really interesting. It was done by this guy Rails back in 2003, and he continues to revise it, and he calls it the Earth Scientists periodic table. And I recommend people go and have a look at it because it's really interesting the way that he's organized elements. They sometimes occur in more than one area. He's really had a pretty big think of it. So I would recommend going to check it out. The first topic that I want to touch on is called electronegativity. It's a word that you probably remember, but likely don't know why it's important in the context of exploration and mining. More importantly, it's used to predict bonds between different elements, whereby ionic bonding will maximize electronegativity difference, and covalent bonding will minimize the difference. And so in this diagram of the periodic table, you can see it's called the Pauling scale of electronegativity of each element. And so really the useful concept to keep in mind here is that you can use this to predict bonds between different elements, whereby, like we said, ionic bonding has high electronegativity difference, covalent bonding minimizes this difference. You can look at the physical and chemical properties, including hardness and cleavage of a compound. This depends on the character of the bond. And also solubility in water is one of the properties that is largely influenced by the nature of the bond. Another concept would be ionic radius. And this is directly applied to how we substitute elements in minerals. So if you've ever thought, hey, why do we see rubidium in K feldspar? It's because it fits into the radius into the site that the potassium occupies. I think this table is just really, really cool. I found it in some old course notes from Linda Bloom. Just as a guide, everybody take a little screenshot or come see this one later. I think a really cool graphic to also understand that it comes down to chemistry, right? They're there for a reason. And then following and adding on to this, ionic potential is also important. Basically, ionic potential, charge divided by radius, it's important because a lot of geochemical behavior depends on it. So ionic potential will give a sense of how strongly or weakly the ion will be electrostatically attracted to ions of an opposite charge, and to what extent the ion will repel other ions of like charge. Some implications will include how it can affect igneous crystallization and how it controls the behavior of cations in solution. I included here actually this table, and it looks really old because it's from a paper in 1963, but actually as a predictive tool, it can help us to answer how our gold, for instance, is traveling in solution. And so when we think of copper deposits, the copper just doesn't appear in a pore-free copper, right? It has to get there somehow. It complexes with an ion, and pore-free copper typically is chlorine because of a high temperature. But it's just that it travels with a in complex with an anion, but then also there are conditions by which it will come out of a solution. And so this slide I've included just to highlight to you guys that these diagrams may or may not, depending on who you are, look a little bit scary and a little bit, not usual for us in exploration or mining to have a look at. But really, the reason why in this case gold is traveling from one place to the next is because of pressure, of pH, redox, temperature, all the different conditions you want to think about. But at one point, it will dump out of solution because something has changed. And a lot of times just looking around mineralogically, you can start to piece together why that's happened. So understanding these different concepts in geochemistry is really important. And like I said before, to just start to plot up things and be like, okay, we have gold here, we have copper here. It's important to ask why they're there. And then again, these fundamental principles are crucial. Okay, so one thing I just wanted to throw in there because I thought that it would be useful to at least a few people here is a lot of times I get the question, which digest should I use? And why shouldn't I use Aqua Regia when doing my drill hole data, my rock data? And so when you're thinking about what digest you should use, it's always important to think about, well, what phase am I targeting? So if you're trying to figure out what's happening in your carbonate phase, well, then yeah, you're going to use a weaker leach. And when you're talking with your vendors, you're talking with your lab, these are conversations that you should be having with them. Overall, when we're doing our drilling data, we definitely want to be using a 4-acid because of the fact that we're trying to break down silicates. We're trying to understand what the whole rock composition is more or less. There are things that are resistant minerals like zircon, for instance. So you won't, while dissolving a lot of the rock, you won't get out completely all the elements. That's always going to be something you're going to have to deal with. But you do get a really good idea for what's going on. And I really just wanted to take the time just to make that point. If you are drilling and using Aqua Regia, you are not getting all the information that you could out of your rock. You are, in my opinion, you're wasting money. Like you're leaving money on the table. When you are assaying your rocks, this is an asset that belongs to your company, and you are losing value by not having the best data set that you can. You've drilled a hole for $1 million, and to back off because it's $20 more to do a 4-acid. All right, that's my TED Talk. Last thing that I wanted to do before I start to look at a few things of how these join together, because I think we have now probably like 20-ish minutes, no more, right, Jess? Yeah, okay. So the last thing I wanted to just do here was really just to throw up just a bunch of terms again. I think a lot of us, especially as we get longer in the profession, we tend to take for granted what a major element, a minor, or a trace element is. But I think a lot of times we'll often say, okay, well, we'll use this one, it's immobile in the system, and therefore we can do some of our chemostrat using zircon as a conserved element. I've just said a bunch of words that have just flown over people that I'm working with's head, not because that I'm trying to sound too smart or something, but it becomes part of our daily lingo. And so for here, I just have just some basic definitions for what an immobile element is. They're typically hosted in these resistate minerals like rutile, zircon, apatite, titanite. And really the important part about them is that despite hydrothermal or weathering processes, these elements are going to remain in the host mineral. And so therefore we can use these to try and document and classify the original hydraulic processes that have happened in rocks before they've undergone alteration. So it's so important when we're working in mining and exploration systems, because we want the hydrothermal alteration, right? And if we're working in some rocks that have been metamorphosed, a lot of stuff has happened. but the best that we can do is to work with these immobile elements. We'll also talk about the large ion lithophile elements, the high field strength elements. And these are just some definitions that I've left in here for people to refer back to. Again, we're not trying to exclude anybody. Compatible versus incompatible. If you guys remember from school, the Bowen's reaction series, it's just during the progressive cooling of magma chamber, elements like silica are progressively enriched during the crystallization of a magma in a closed system, so they are incompatible. And elements like calcium, magnesium, iron, these are all depleted, so they're compatible elements. And that's all it is. I stole this idea from, I think, an SCG slide. I really loved it. Just highlighting on you where these immobile elements are. If you go into iogas, for instance, though, they'll be all like documented already, so you don't even really have to think. But otherwise, here are the mobile elements that we'll typically use. Also, you can't see it too well, but aluminum in there is typically conserved as well. And to do this kind of work where you're trying to track what the original rock is, hydrothermal, you need to be using a 4-acid data set. Let's not even consider using aquaregia for this. And then likewise, you have these mobile elements. There is more of them, but in general, when we're talking about the rock forming elements, these mobile elements are hosted in minerals that have more ionic bonds. We talked about ionic bonds a little bit. And these are typically altered during hydrothermal, alteration, weathering, metamorphism. And so really, that's all they are. That's who they are. So just say hi to them. There's lots of other different types of things. If you Google anything, Pathfinder elements or whatever, like you can find them, but just don't ever not ask, at least to me, never don't ask me a question because I've said a term that you don't know what it is. All right, so my last part of this is better together. Geochemistry and hyperspectral. Maybe somebody gets the reference, has listened to Jack Johnson at some point, who knows? But yeah, better together. Just one thing I wanted to say, and I got a lot of questions about this over many years now. When we talk about composite techniques, composite analyses, that would be something like what you do for XRD, for lithogeochemistry assay. We're crushing a rock to a fine powder, and we are taking a composite sample. We're sampling it in a very homogeneous way. So we're taking something heterogeneous, making it homogeneous, and that's how we're doing it. With hyperspectral, though, we are using a surface technique, whether you're doing airborne satellite, Hyperspec, any kind of imaging system. It is a surface analysis. And so for a single point, maybe you can say, okay, this whole section of rock cannot just all be montmorillonite, cannot all just be chlorite, but that's what's come out in your single point measurement. That's why you have them over drill holes and everything to get an idea of what's happening in your system. But when you start getting into imaging, then you're starting to really get a good idea of, it's not whole rock, but what is happening in the rock as a whole, I would say. The two themes that I'm going to touch on in this section, how does hyperspectral tie in with fundamental geochemical principles, and just a few practical looks at what this looks like. Mineral chemistry is a fluid proxy. So this is a classic diagram by Corbett and Leach, where it's really for porphyry epithermal systems. These are just different mineral assemblages. Over here, you have increasing temperature versus increasing pH. Oh my God, I see somebody has a little smiley face jumping up over there. Yeah, I know, crazy, Corbett and Leach. But really, what's cool when you're looking at all this mineral chemistry stuff, it's like a fluid proxy, right? Here we have a mineral class map, and all that is just a summary of all the minerals that are in this image. In pink, we have gypsum. We have these blues are different crystallinities of white mica. We have keolinite, and we have a little bit in lavender of the montmorillonite. But what I have here is white mica composition, and we're looking at here in reds are trending towards maybe phengites, and here's in the center our vein halo that we have is more muscovitic, And then also here we have chlorites, which the chemistry here we're looking at is increase in magnesium, gets more bluish, which is what we're seeing over here. So it is to say that we're looking at these, especially when we're looking at them in images where it just really jumps out at you. When we're looking at this data, we can already be thinking like chemically, geochemically, geologically, where are we sitting in terms of PTX space? They tend to be overwhelming looking a lot of times. There's scale bars, there's arrows. This one at least has some colors in it, but really never fear a diagram that's in a geochemical paper. There's always a lot of information in there. Simply put, all this diagram at the left is explaining is how, in this case, is why we found extensive propylite in this system over here. This is a porphyry system. I want to say, I think it's in Peru, but it's just explaining why there's propylite at a greater than a kilometer depth. And if you look back to over here, you can see the propylite fields over here. What was our starting composition? This graph, a diagram I pulled from paper. I didn't create this for this situation. And so it's just, what was our starting composition of our fluid? And then really, how did temperature, not really to extent necessarily over here, pH, but like how did temperature really change to get us into the propylite zone? So it's just fluid cooling, and that's why we have it there. We no longer have some of these other minerals. We're up now to this kind of PTX space. It's really important that we know our magma starting composition, and we can then really track and understand why we're seeing things that we really didn't expect to see. Because propylite, we tend to think of advanced argillic and nothing else. I'm not saying that's not, but I'm just saying that it's here due to fluid cooling. I love this one. So a dark rock clay story. You look at this, it comes from a high sulfidation system. So I will say that. But as for what this contains, besides to me, probably quite a bit of pyrite, it's not really clear what's there. Throw on top, this is a mineral map that's courtesy of CoreScan. And what you have in here is in this light pink, you have alunite, and this dark kind of mustardy color is kaolinite, and you have a little bit of dickite in gray. And now we're throwing another diagram on top. This one, again, didn't create it for this situation. It's just from a paper. But here, what we can do when we're looking at this mineral assemblage, and again, it's really important to understand your rocks, maybe have some thin sections made up. Are these in equilibrium? That's important to think about as well. But in context of how this rock has journeyed through its history, we're starting to see changes potentially in oxygen fugacity. So is it an oxidizing environment? Is it a reducing environment? Is it more oxidizing than it was before? And then also, there's also pH changes as well. Kaolinite is a more neutral mineral compared to alunite, which is much more acid. There's just lots of things to think about when you see either these hyperspectral imaging data sets, your hyperspectral point data, or even just looking at the core in general. There's a lot of geochem happening, a lot of fluids. Bringing back this diagram, again, something else that I want to throw out in here that I thought was interesting is that in the same area, again, not that they're co-occurring, but in the same area over here, we have kaolinite and dickite. This assemblage, to have dickite, it's a higher temperature mineral, and to get to kaolinite, it's just lower in temperature. So the same actual mineral formula, both aluminum and silicates, but they're governed by temperature. And with hyperspectral, you can definitely tell the difference between them, which makes it really cool. It gives you a lot more, I guess, context in your deposit to really see all those changes as you perhaps approach ore. And the last one that I wanted to throw in this example, in terms of tying hyperspectral results to chemistry, this over here, there's not a crazy amount of change necessarily. in the, whether it's a sodic rich or potassic rich alunite, but there are distinct changes that you can have in your alunite. And this is all just fluid chemistry. This is what we're talking about. It's really important that when you're looking at any data set, you also are tying it back to fundamentally basic principles of chemistry. I know that you guys are thinking, but what am I seeing in my data? And so these last few slides are just devoted to that, and that's where I'll leave it. But this would just be a very typical potassic alteration versus sodic alteration diagram. Really, in the middle here, you're looking more at your least altered rock, and then as you're trending this way, you're looking at more biotite-rich alteration, muscovitic alteration, montmorillonites down here a little bit. You have illite, that's its tie line, and then also you have your sodic alteration more trending towards your albite. In your rocks, if you're using a geochemical analysis package for us to digest, ICP, you can produce pots seen just like this. This one came from a course given by Scott Haley. You're going to help track your alteration changes, and a degree, it can definitely aid in mineralogical interpretation and identification. But the addition of hyperspectral can definitely augment this by providing some additional mineralogical information as well as crystalline mineral chemistry information. And always the way I would think about it is that spectral mapping, whole rock geochemistry, both have their strengths and weaknesses, which we'll look at in the next slide. But these data sets are completely complementary, and it's not going to be one or the other. Here you can see I put a little table together just looking at some porphyries, typical mineralogy that you might see, lithocaps and into the potassic zone. You have some that are difficult to pick in biotite, a bit difficult to pick in assay, but it's recognized easily in hyperspectral, and you can also get chemistry out of it. Is it an iron-rich biotite or a magnesium-rich biotite? And the list goes on. It's just more than reading you this. These are complementary techniques. And by having both, you're just improving the value of your data set. Mapping alteration versus mapping mineralogy, just like I said. In this one, I also pulled this from one of Scott's courses. And in here, what you have is you have your ICP 4-acid geochemistry underneath. You can see your trends to a degree. Like we said, you can identify your mineralogy. But over the top of this is mineralogy that was determined using a core scan data set. And this one over here was the same diagram we looked at earlier. And this is just another diagram. You have potassium, magnesium, aluminum. This ternary plot is another one that you can use for looking at your porphyry or acid environments. It's really what it's doing is differentiating advanced argillic alteration, which you would see up in here. You have your prophyllites and your alunites up here versus your sericite, white mica, chlorite clay alteration down here. And my final slide, I just wanted to throw this one out here for you guys. I did this for a talk last October, I want to say. There was a lot more slides that went into this, but the sum total of all of this would just be that I did some work. I got some domains, some mineralogy domains, all the ones that I'm going to play this for you, actually. Hold on. Oh, there we go. All the ones in green are all kind of amphiboles, biotites, epidotes, a little bit of iron carbonate. And in yellow, you have kilnites, muscovites, prophyllites, featureless slope, which is a mixture of anhydrous quartz and anhydrous feldspar. And then in purples are your iron oxides and some additional, say, illites, crophyllite, top of your supergene. But, oops, wanted to play it for you guys again. I guess it's not going to happen. But the point here is that also I use Leapfrog in order to both model these, but then also to model these domains, but then also to just only show where we have the copper 2% shell. And what's important about this is that if you look at some of these, not so bad in this deposit, I would say, but in other ones, you look at some of these minerals and you have keolinites, some prophyllites, fluorites. Like, these minerals can have impacts on your processing. So understanding, and not necessarily that this is giving you exact percentages of how much is there. You can perhaps use your chemistry to try and work that back and try and create some really nice shells for that. But what it's showing you is its distribution. So if this is your copper shell and you're dealing with quite a bit of montmorillonite or illite or perophilite, these have implications. So combining these together and using these in a meaningful way it's just really powerful, and I'm really happy to be part of the community. With that, I want to thank everybody.
Thank you so much. There was so much useful stuff in there. So I'm so grateful that you've spoken to us today.